Question 2, and we're now looking at power. So we've got here a car of mass 800 kilograms which is moving up an incline. We've got a constant resistance to motion, and we've got two instances, one where the car's moving uphill and the other where the car's moving downhill. In both cases we know that this is a power question, so we're going to be using that power is equal to force multiplied by velocity. Now in both cases here I've got power and velocity, and I'm going to just rearrange that into power divided by velocity, which is going to give me my force in both cases. So this is what we're going to use to answer the question. Now we're given two different instances, one where we're moving uphill and one where we're moving down, so I'm going to draw two different diagrams just underneath my question here. One for when we're moving uphill and another for when we're moving downhill. So this is the case where we're at 12.5 meters per second uphill, and this is the case where I'm at 12.5 meters per second downhill. In both cases my angle here is theta. I've got my car which has mass 800 g, that's the same in both cases. And as always with these sorts of questions, I'm only interested in motion that is parallel to the plane, so rather than worrying about just the vertical part, I just want to think about the bit here that's parallel and pushing down in this direction, which we know from having done this hundreds of times is going to be 800 g sine theta, and because sine theta works out to be 1 over 20, as we're told from the question, this is 800 times by 1 over 20, which gives me 40g. Exactly the same in the downhill case. I'm going to have 40g that's pulling me downhill. Now, when we are moving uphill, we know the resistance to motion is going to be downhill, and that's going to be my R value. When I'm moving downhill, I know my resistance to motion is going to be uphill, so that's going to be my R value. Now, as I wrote down earlier, we have these two different power equations, so I'm using my power equation here, and when the car is moving up the road with a constant speed of 12.5 meters per second, the power is 3p, so that's going to give me 3p over 12.5 for the driving force forward. And conversely, when it's moving downhill, I've got p over 12.5, which is going to give me the force moving downwards. So just looking at my questions here, when I'm moving uphill, the force was 3p over 12.5, and when I was moving downhill, my force was p over 12.5. I've got two systems, so I've got simultaneous equations here. From my first system, resolving this, I'm going to end up with 3p over 12.5 is equal to R plus 40g. And from my second system, I've got that p over 12.5 plus the 40g is equal to R. Now what I've chosen to do here is to rearrange this equation to give me 3p over 12.5 minus 40g is equal to R. So now I can set the two equations equal to each other. So that's to say that 3p over 12.5 minus 40g from my uphill equation is going to be equal to p over 12.5 plus 40g from my downhill equation, which I can then rearrange. 40g I should have on here. Rearrange, subtract the p over 12.5 to give 2p over 12.5 is equal to 80g. Now if I multiply through by the 12.5 and divide through by 2, I end up with p is equal to 500g. Now all I need to do is to substitute that back into either of my equations to find out the value of R, and seeing as the downhill equation was already set up in terms of R, so I'm going to have R is equal to this p value, 500g, over 12.5 plus 40g, which turns out to be 40g plus 40g, which is 80g. So those are my answers for P and for R. Obviously we could work those out as numerical values, but I've just chosen here to leave it like that for speed. Right, moving on to part B. When the car is moving up the road at a constant speed of 12.5, the engine is switched off and the car comes to rest without braking. the distance in a distance d meters. The resistance to motion of the car from non-gravitational forces is still modelled as the constant force of magnitude r newtons. Using the work energy principle, find out the distance d. Okay, so I'm just going to draw a new diagram at the bottom here. So I'm going to have my car travelling uphill, 12.5 meters per second, and we're going to travel to this point here, which is a distance of d away. Now, using the work energy principle, I know that to start with, I have kinetic energy, and I know that through this process I'm going to convert that kinetic energy into work done against the resistance and gravitational potential energy gained. So my work done is going to be the force, which is going to be r, the resistive force to motion, times by the distance, which is d. Now thinking about kinetic energy, that's the easy part. That's just going to use my 12.5 from here. So we've got a half times the mass of the car times by the 12.5 squared. And then finally I've got this GPE, so I just need the height gained. And that height gained is going to be d sine theta. And we know that the formula for gravitational potential energy is mg delta h, so that's 800 g, and then the height climbed, d sine theta. I need to add those bits together. On the left hand side I have plugged into my calculator to get 62,500 is equal to r times by the distance. Well, we worked out r from the previous question, which was 80 g times by d, and we knew that sine theta here was 1 over 20, and so 1 over 20 times by 800g gives me 40g times d. So skipping a couple of steps, I've got 62,500 divided by 120g, which is going to give me my value for d, and popping that onto my calculator I get a value for d which is 53.1 meters. And that's it for question 2.